You know how security cameras work? They don't wait for something to happen. They just keep watching day and night so that when something does happen, there's a record of it. Now imagine that but for the universe. No one pointing it, no one choosing targets, just a system that scans everything over and over without blinking. Every few seconds it captures a new frame. Every few nights it has observed most of the sky and then it starts over. In its first few hours of testing, it found over 2,000 asteroids we didn't even know were there. Some were close, some were fast. All of them were missed until now. It doesn't zoom in. It doesn't wait for instructions. It just watches because space doesn't warn you before something happens. And now, for the first time, we're not going to miss it. Most people think telescopes are slow. You point them at one star, one galaxy, and wait. Maybe you're lucky and catch something interesting. Maybe you spend the night getting nothing. That's how most of astronomy has worked for centuries. Tiny patches of the sky studied one at a time. But Rubin doesn't work like that. This thing doesn't sit around waiting for instructions. It has one job, to keep watching a wide swath of the sky constantly. So, how do you even begin to build something like that? First, forget everything you know about telescopes. Rubin isn't some long metal tube with a guy peeking through the end. It's a completely different machine. The official name for it is the Simony Survey Telescope, the main telescope of the Vera Rubin Observatory, a next-generation astronomical facility. The development of the Vera Rubin Observatory has spanned more than 3 decades, driven by a bold vision to transform astronomy through an unprecedented wide-field, high-resolution survey of the cosmos. The Rubin Observatory is a collaborative effort led by the U.S. National Science Foundation, the Department of Energy, and international partners from around the world. The observatory's design was driven by the goal of conducting the Legacy Survey of Space and Time, a 10-year survey to image the entire southern sky every few nights, producing an unprecedented data set of billions of galaxies and celestial objects, significantly advancing cosmology, solar system studies, and Milky Way research. Construction began in 2015 on Cerro Passion in Chile, about 8,800 feet above sea level, where the air is thin and the skies are clear almost every night of the year, ideal for astronomical observations. Location matters. You don't build something this powerful just anywhere. But it's not just where it's built, it's how it's built. The mirror at the heart of this telescope is 8.4 meters wide. That's bigger than the mirror on Hubble. But size isn't the most interesting part. What makes Rubin's optical system different is that it uses a unique 3-mirror anastigmatic optical design, primary, secondary, and tertiary mirrors. Most telescopes use a single mirror and get a narrow cone of vision. Rubin's 3-mirror design gives it a huge, flat field of view spanning approximately 9.6 degrees, large enough to capture about 45 full moons in a single snapshot, enabling rapid sky coverage. And then you pair that with the largest digital camera ever made, no exaggeration, 3.2 gigapixels. The sensor itself is nearly the size of a car's steering wheel. It's made up of 189 CCD sensors stitched together into a single focal plane. The camera alone is over 3 tons. They had to design a whole new cryogenic system just to keep it cool enough to work properly without overheating. Now, you might wonder, why build a camera this big if you're just going to scan the sky every night? Why not take smaller targeted images like everyone else? Because Rubin isn't looking for what we already know. It's trying to catch what we're missing. And the only way to do that is to be faster and wider than anything before it. Rubin can take a full shot of the sky in 30 seconds, move slightly, take another, and repeat. It cycles through 6 filters, optical to near-infrared, and by the time it's done for the night, it's collected tens of terabytes of data every single night. This isn't the kind of telescope you wait to use. It's fully automated. It's pre-programmed to scan, log, repeat. All the raw data goes into a giant pipeline where it's cleaned up, stitched together, and flagged for changes. Did something move? Did something flash? Did a star suddenly get brighter? A program flags it. Artificial intelligence, critical for pattern recognition, manages the vast data set, identifying changes among billions of objects, comparing them to previous data, and alerting global telescopes in real time for follow-up observations. And this process happens without human input. Which brings us to something that really matters, the fact that Rubin will collect more data in its first year than every other telescope on Earth has gathered in decades. That's not just a claim. That's the reality of imaging the entire sky over and over again with a 3.2 gigapixel camera. Let me put it this way, Hubble takes incredible deep shots of distant galaxies, but Hubble sees a tiny sliver of the sky. Rubin trades zoom for coverage. Instead of seeing one galaxy in detail, it sees tens of thousands at once, over and over, to track how they move and evolve over time. And unlike Hubble, Rubin won't be pointing at just one thing. It will do the exact same scan again and again for 10 years. That means we're not just seeing the universe as it is, we're recording how it changes, like a cosmic time-lapse. Think about how many times we've missed major events in space because no one was looking. Supernovae that happened and faded. Comets that passed us by. Asteroids that snuck in from the blind spot. Rubin is designed to remove that blind spot. It's not waiting for something to happen, it's already watching. And by the time most people hear about a discovery, Rubin's camera probably caught it days ago. Rubin just had what's called first light. That's the term astronomers use when a telescope finally starts observing the sky for real. Not calibration tests, not dummy runs, real exposures. And Rubin didn't waste any time. It started scanning, and within the first few hours, it delivered. Over just 10 hours of early operations, Rubin's camera captured more than 1,100 exposures. And in that short window, it detected over 2,100 previously unknown asteroids. That's not a typo, 2,000 in one night. Most of those were harmless. A few were flagged as near-Earth objects, which means they're in the general neighborhood, but nothing dangerous yet. Still, the point is clear, these were objects we didn't know about. They were out there moving fast, and we had zero idea they existed until Rubin picked them up. And that was just from the motion detection. That's one part of what Rubin does. But it also delivered full-resolution, wide-field images that honestly looked like stitched mosaics from space, except they weren't stitched. They were just single frames taken with the massive sensor. One of the highlights was a shot of the Virgo cluster, a region packed with thousands of galaxies located approximately 55 million light-years away. Rubin captured millions of galaxies in a single view. This single view showcases a variety of galaxy types, including spiral, elliptical, and merging galaxies, with foreground Milky Way stars and distant galaxy groups visible. And it didn't stop there. It also imaged the Trifid and Lagoon nebulae using a combined 678 exposures. That one image revealed shock waves, dust lanes, and structures in star-forming regions that look like something out of a science fiction movie. But again, that's what the camera really saw. It's raw reality in detail we've never had before. But here's the thing, these aren't discovery photos. They are proof of capability shots. Rubin's not here to take pretty pictures and move on. It's built to take that same shot again and again over time and log the differences. Earth has a blind spot. For all the satellites we've launched, for all the telescopes scanning the night sky, we still don't have a complete list of everything that could slam into our planet. Not even close. In fact, by NASA's own admission, we've only catalogued around 40% of the near-Earth objects that could actually do serious damage. And by serious, we're talking about city-killing or even continent-level impacts. Think that sounds dramatic? It's not. In 2013, a 20-meter-wide asteroid exploded over Chelyabinsk, Russia, with the force of about 500 kilotons of TNT. That's more than 30 times the energy of the Hiroshima bomb. And no one saw it coming. It came from the direction of the sun, completely invisible to telescopes that only observe at night, and exploded in the air, shattering windows and injuring over 1,600 people, mostly from flying glass. Now, imagine if that rock had been twice as big, or made it to the ground, or hit a more populated area. The point is, our planet is not immune. The only reason it doesn't happen more often is dumb luck. So that's where Rubin comes in. Because Rubin isn't just another space telescope. It's fast, it's wide, and most importantly, it's consistent. Let's go back to those early test images. In just 10 hours of scanning, Rubin spotted over 2,100 previously unknown asteroids, not confirmed ones, new ones. Many were just bits of rock out in the belt between Mars and Jupiter. Some were near-Earth objects, and those are the ones that matter because all it takes is one small, fast-moving rock with the wrong orbit, and the clock starts ticking. The thing is, most telescopes miss these. They're not built to scan for motion. They're built to stare and gather light. But Rubin's design, its cadence, its field of view, and the speed of its imaging system means it can catch objects that move between exposures. It doesn't just take one picture and walk away. It looks again, then again, and if something's changed, even a few pixels worth, it flags it. Rubin is expected to find millions of new solar system objects over the next decade. That includes everything from main belt asteroids to outer system comets to objects in weird tilted orbits that don't fit anything we've seen before. And buried in that pile could be the next serious threat. But the real value here isn't just spotting these objects, it's spotting them early. Because time matters. If you discover a dangerous asteroid 2 days before it hits, there's nothing you can do. But 2 years, 10 years, that changes everything. You can model its orbit, track it, plan for a deflection mission if needed, or at the very least evacuate a region before it gets obliterated. Rubin gives us that time buffer, not for all threats, but for more of them than we've ever had a chance to catch before. And it's not doing it alone. The data Rubin collects is shared with the Minor Planet Center and other observatories around the world. Once an object is flagged, others jump in to refine its orbit and get a better read on its trajectory. That global coordination didn't exist during Chelyabinsk. It does now. You don't name a $700 million observatory after someone unless they change the game, and Vera Rubin did exactly that. Most people outside the astronomy world don't know her name, but they probably know about dark matter, that invisible stuff that supposedly makes up most of the mass in the universe. Yeah, that idea exists because Vera Rubin proved something wasn't adding up. Back in the 1970s, Rubin wasn't working with billion-dollar telescopes or supercomputers. She was doing something deceptively simple, measuring how stars move around galaxies. You'd expect the stars near the center of a galaxy to move faster and the stars on the outer edges to move slower, just like planets in our solar system. That's basic Newtonian physics, which predicts that orbital velocity decreases with distance from the galactic center. But that's not what she saw. Rubin found that the stars on the outskirts of galaxies were moving just as fast as the ones near the center. In some cases, even faster. That was impossible unless there was something else out there, something we couldn't see. This implied additional mass exerting gravitational influence. She wasn't the first person to suggest missing mass, but she was the first to prove it over and over across different galaxies with better data than anyone had collected before.